Okay, so I think we should be set. All right, welcome. Welcome to Friday, the end of the first week, which is a good thing. I wanted to just pull up the course Moodle page to point out some things, just so we're all at the same page with kind of how things are going to work. So we have now, because we're done with week one, so I have at the top of week one kind of the checklist for this week. There's the in-class, which we did, you all did and handed in, so you're done with that, great. If you were to miss one of those at some point, this is where you would find it. If you get halfway done in class and have to turn it in later, this is where you could turn it in afterward. So this is where you can find it. You can also find after people turn them in, I'll post solutions to those so you can go back and check and see what you did. Okay, so that's where that will live. I posted our first homework assignment here. As part of that homework assignment, so this homework is due in a week. We will typically have homework assignments due kind of like at class time. So plan on like finishing it up Thursday, but I'll just have it, if you want to hand it in, sometime Friday morning, that's fine too. For the sake of our grader, she would prefer us to all upload like a scanned version of our assignment to the little assignment link, like you all have done for other classes, and like most of you did for thermal. So you'll upload your scanned PDF of your assignment there. Okay, for this assignment, and I don't know how often I'll do this. I'll try to do it at least a couple times. I have a video that kind of goes along with the assignment. You don't have to watch the whole thing, like the first 13 minutes. I think it's kind of fun. We'll watch more videos from this series because this is one of my favorite things about fluids is this video series. It's like I think it's from the mid 50s. And as you watch it, just realize like this is from the 50s. So everything that you're seeing is not like an animation. It's just like, a video camera filming something. So it's wild. So you'll see stuff and then all of a sudden it'll feel like it's an animation and they'll be drawing on things. And then you like see a hand reach in and you'll be like, oh, they were just drawing on like a piece of glass with a marker. And that's how they're like doing all the animations and stuff. It's pretty fun. So this is one of them. It's about flow visualization. So some of the stuff that we talked about last class, this should hopefully help you see visually some of this stuff. So I think it's useful. We'll continue to have some of this stuff kind of sprinkled through. The homework assignment itself is fairly short, but if you find yourself like running stumped on some of it, I think it's easy once you get it, but if you don't like get the hang of it, then it's not. So make sure if you are struggling or having questions, pop in the help session, shoot me an email, something like that. Hopefully then you'll get the hang of it and then it will be easy. And you can see it's hidden from you guys right now, but I have a solution there. And that will typically be the case. So whenever you hand in your homework assignment, maybe like a week later or so, I'll post the solutions to that. So for studying and for exams and stuff, you'll be able to have those. I also have the lecture video. So I'll be recording lecture videos if you want to go back and watch something, if you miss stuff. I also have, if I do show slides, I'll try to post those as well, or at least the ones that I think are useful for you to have. So that's where all that stuff should live. Hopefully it's organized in a way that makes some sense at least. Okay. So, so what we're going to be talking about today is a little bit more on streamlines, because that's going to be something that we use. It's probably going to be our most useful tool to be able to connect what we see visually with what we can do mathematically. It's this tool of streamline. So we'll do quite a bit with it. So these are our kind of 3 different points about streamlines. So you probably have these written down already. they're tangent to the velocity field. They are, so the velocity is perpendicular, right? That's the same thing. But the velocity magnitude can change along a streamline. So if we were to look at some sort of flow, I'll just draw this. Let's say we have a corner like this, and we have a fluid flowing in that corner. Okay, what would that look like? Your fluid would come and go maybe something like that. So those would be the streamlines. And if we wanted to draw velocity vectors on that, we could have something like, initially it's going down that way, then it kind of turns. It's kind of a bad one. Then it turns again, right? And we could draw velocity vectors at any point on this, and they would always be, at any point they're going to be tangent to that velocity or to that streamline. So rather than trying to draw the velocity vector, right, you can kind of see, it gives you a visual picture of like where the flow is going. One of the key things that hopefully you found from the in-class thing, we have these different ways of talking about or seeing flow experimentally. Timelines, path lines, and streak lines. Those are our three ways of actually like doing an experiment and seeing what's happening. The cool thing is if we have steady flow, streak lines and path lines are streamlines. So if you like inject a dye into a flow and watch where that dye goes, that's a streamline. You'll see some of this, especially when you watch the video for the homework, you'll see visually how some of this fits together. Okay, so what is our way, again, this is to try to connect like visual stuff to some of the vector math. So how do we actually do that? If we look at what our vector math would be, so our key point is the streamline is tangent to velocity field. Okay. So if we know the velocity field, we should be able to figure out the streamlines because they're related, they're tangent to each other. So how would we actually do that? So if we have a streamline, right, that's, let's just draw I'll draw it more curved so that we get a little bit better. So this is our streamline. This is our velocity vector at that point. Okay, we can write our velocity vector v equals, right, this is our notation, u I hat plus little v j hat plus w k hat. So that's our vector notation for the velocity. Our streamline has to be tangent to that. So it has to be pointing in the exact same direction. Right? So if we looked at a really small chunk of the streamline, it should be pointing in the exact same direction. So a small we'll call that a really small chunk of the streamline, we'll call it ds vector. It has to be pointing in the same direction, and it's going to have size dx I hat plus dy j hat plus dz k hat. Okay, and I'll kind of zoom in. It might be a little tricky to draw this, but I'll zoom in and draw on our little diagram what that would look like. So that would be like right here, you know, pointing in the exact same direction. That's D. This is way bigger than it really is because it's a differential thing, but it's a differential thing pointing in the exact same direction. Does that kind of make sense, right? They're tangent to each other. They have to be pointing in the same direction. We're just taking our streamline, dicing it up into teeny tiny bits and saying, what direction is that? It has to be the same. So if these two are the same, then the ratio, like the relative ratio of, you know, how far is V pointing in the U direction compared to S in the X, like, so U and dx, how far both of them are pointing in the X direction, those have to be the same amount relative to their total length. Same with this, like how much is it in the V direction, or how much is it in the Y direction in both of them, and how much of them is pointing in the Z direction. So they have to be like scaled just by some constant, right? Because they're the same direction, just different size. So everything should just be able to be scaled by a constant. So the equation that we can use for that, and I'm just going to write this rather than deriving it. We could derive it from vector notation. But I think you'll hopefully be able to see just from some of that simple argument. So the ratio of the size in the X direction has to be equal to the ratio of the size in the Y direction, has to be equal to the ratio of the size in the Z direction. Right? This equation is the same as saying all the directions have to be scaled by the same constant. Right? If the vector V is 100 times bigger, it's 100 times bigger in every dimension. So this ratio would be 100, but it's 100 for all the directions. So this equation is our differential equation for streamlines. Right, and it's a differential equation because it has those differentials dx, dy, and dz. Hopefully you can just kind of convince yourself that this is just a scaling between the two things. We could also go through and, you know, we could also derive this from V cross ds equals 0. So we could do a more mathematically rigorous definition, although they're the equivalent, by doing the cross product between these two vectors and saying that the cross product has to equal 0 because they're tangent, so there's no perpendicular component. And we could go about doing that. Okay, so we'll put this on hold for just a second. And we'll come back to this again in just a second. Figuring out, so this will be a way for us to be able to like take some velocity field and figure out what the streamlines look like, and you know, vice versa. If we have streamlines, we can figure out the velocity field. So this is going to be a way to get back and forth between the two. So we'll call this a quick aside for so this equation, the definition of the differential equation for streamlines is a three-dimensional thing. But a lot of times we're going to try to simplify things down to being either one-dimensional or two-dimensional rather than having to deal with 3 dimensions. So we'll take kind of a quick aside and just remind ourselves what we mean by that. So simplifying the flow to 1D or 2D simplifies our problems, it simplifies our math, it makes our lives easier. So it's a useful thing. If we have some examples, so this was, I think it's easiest to see with some examples. So this would be flow, and we'll use this quite a bit. Because it's a flow that does come up quite often in real life. So flow between plates. So we have a top plate and a bottom plate. Say they're separated by some distance here, the gap B, and this top plate is moving in the x direction with a velocity u. So let's put some coordinates on this. So this is the y direction. That's the x direction, and that's z. Okay, so what does the flow look like? Again, we talked about this briefly, but right, the no-slip boundary condition means that if the bottom's not moving and the top is, the fluid is stopped at the bottom, the fluid is moving at the velocity big U at the top. And it turns out it's linear in between those 2 points. So we have a flow that looks like this. So this is that's our fluid. Okay, so we have a flow that looks like that. It's nice and linear from 0 to big U. The equation, or if we want to look at this, so we do have, obviously, our fluid is 3-dimensional, right? It's left and right, top and bottom, in and out of the board, right? This is like a thin gap that comes in and out of the TV quite a ways, or in and out of your page. The question is, in which direction does the flow or does the velocity change? So if this is the case, your velocity in and out of the TV or in and out of your page is not changing, okay? If you come from like right in line with this, or if you come out a foot, we're assuming that nothing happens, there's no edge, it just is the exact same as what it was before. So our flow is not changing in the z direction. There is still fluid there. It's also not changing in the x direction, right? So if I'm at this point here, that's my velocity. If I'm over here, right, my velocity is still the exact same, right? So as I move along in the x direction, our velocity is the same. So the only direction that the velocity is changing is if I move up and down in the y direction, right? So this is 1D flow changing in y. And we can actually write the mathematical equation for this, right? Our velocity field. And we'll be able to derive this later, but if we wanted to write what our velocity field is, it's big U y over b I hat. Okay, so if we look at this equation, our velocity is pointing in the x direction because it's in the I hat direction, but it's changing in the y direction. So changing in y pointing in X. Okay, let's look at one other quick example. So let's look at, this is flow in a diverging pipe. So we have something that looks like this. Right, so we have a pipe that kind of is expanding out into a nozzle, and I'm assuming like it continues on to the left and to the right of what we're showing here. Okay, so our coordinate system, we're not going to use Cartesian coordinates, we'll use cylindrical coordinates because we're in a cylindrical geometry. So our coordinate system is going to look like that. So we have, we'll call it X, R, and theta. Okay, this is a, this would be a pressure-driven flow. So this is a flow, this is liquid fluid that's being pushed along by pressure. So what would it look like? It would look in the pipe like this. Right, the no-slip condition means that the fluid has to be stopped at the walls of the pipe. So velocity is 0 at the walls, and it's going to be a maximum in the center. It turns out it's a nice parabola. Again, you have to just trust me on this. For now, we'll solve it and figure that out, that this is what it looks like later. Okay, so that's what it looks like in this constant diameter section of the pipe. So we have, right, some radius, big R. There's a maximum velocity. We'll call that U max. And again, if we wanted to write an equation for this section of the pipe, we could write that the velocity field is equal to U max 1 minus R over big R squared I hat. Okay, and again, we would have, okay, so the velocity is pointing in X, changing in R. So in this section, this would be one-dimensional, changing in R. This next section here, right, we're going to have right, something that looks like let me draw this a little better. So this is coming. So basically, once we get to that diverging section, then we're going to start slowing down. So then we're going to have something like this. We're in this diverging section. We're now in a position where we have 2D flow. So we're now a function in R and X. Okay, it's still only pointing in X, but it's now two-dimensional because it's changing in both radius as you go from the center of the pipe to the outside, but it's also changing depending on where you are in that expanding section. Okay, so the homework that you have will go through like a number of different equations, and you'll be asked, you know, what is this one-dimensional, two-dimensional, three-dimensional, four-dimensional? Is it changing in time too? And exactly what that looks like. So hopefully this helps you sort some of that stuff out. Okay, so we're going to do an example problem and look at how we can use some of the math parts to figure out, and be able to figure out what's happening and how to connect velocity fields and streamlines and particle motion and how to do some of the math of that. So this is going to be example if you want to look afterward, I think this should be example 2.1 in your book. Okay, so if we have a velocity field, which is given by this equation. So let's say our velocity is described by this, a x I minus a y j. Okay, so this is that's our equation. X and y have units of meters, and a equals 0.3 per second. Okay, just as a sanity check, this should work out. So what's the velocity in the x direction? It's going to be up per second times a meter. So the units are going to be meters per second. So a velocity. If we have different looking functions there, you're going to have maybe different units on the constant or something, so that the whole thing, so like this whole term has to work out to units of meters per second because it's a velocity. All right, so we can find, if we have this velocity field, we could find the velocity at a certain point. So at the point 1, 3, velocity equals 0.3 seconds. This would be 1 meter I hat minus 0.3 per second, 3 meters j hat. So V would equal to 0.3 meters per second I hat minus 0.9 meters per second j hat. Okay, so we can do basic things like that. Like if you're given any point, you can figure out what's the velocity. We could figure out what's the speed, right? We could do, so at this point, 1, 3, we are, we're x and y. If we're here at 1 and up here at 3, right at this point, we are, pointing down and kind of that way. If we wanted to on this graph, like we could plot up every single vector or a whole bunch of vectors and get an idea of the shape of the flow. A better way is to do this, is figure out what the streamlines are going to be and what they're going to look like in this flow. So we can determine streamlines. So how are we going to determine streamlines? Well, we have our differential equation for streamlines. So we have the equation u over dx plus v over, or equals, sorry, not plus, equals v over dy equals w over dz. Okay, that's our differential equation for streamlines. This is the equation that we have to solve to figure out the streamlines. Our flow is, right, this is our equation for our flow. Our flow is pointing in both the X and Y direction, and it's also changing in both X and Y. So this is a two-dimensional flow. It's not changing in Z. So we can cross, I'll use blue. So we can cross this out because we have a 2D flow, no change in Z. Okay, so we don't have to worry about Z. We just have to worry about X and Y. So the equation that we're trying to solve is this one. U over dx equals V over dy. Okay. If we want to look at that, what is our equation for U? That's a x over dx equals, if you go back up, equals minus ay, equals negative a y over dy, just plugging in our u and v. And then, yikes. Okay, then we have to do some calculus on this, right? So we're gonna get the dx, dy on the same side. We're gonna do separation of variables and get the x's and all on the same side and the y's all on the same side, and then we can do an integration. So today it looks like we already did that. I'm gonna flip it because we have the like dx and dy on the bottom of our fraction. So I'm gonna flip it, both of those guys over. So we have, right, 1 over, well, I guess we'll call it a over, no, 1 over ax dx equals negative 1 over a y dy. Okay, and then we can simply get rid of the a's because the a's are going to cancel each other out. So we'll multiply both sides by a goes away. So we have 1 over x dx equals 1 over y negative dy. And then we're going to integrate. So we can integrate both sides. Okay, the integral of 1 over x dx equal to what? Natural log of x. Just natural log of x, or anything else that we should not forget about? Plus c, yes, plus a constant. Your calculus teachers are so happy. Okay, so we can't forget the constants, and we'll see why in a second. Okay, so then we'll do the other one, the integral of negative 1 over y dy equals negative ln of y plus c. Okay, so we get our equation should have been, okay, so this is ln of x plus, we'll call this c1, and we'll call that c2, equals negative ln of y minus c2. Okay, and then let's, again, we're trying to rearrange this to be able to like plot lines. So we want it eventually in y equals something of x, like a y equals format, so we could, you know, plot up some lines. So let's get it in y equals format. It's a little bit tricky to do, but okay, so we have ln x plus ln of y equals negative C2 minus C1. And because those are both arbitrary constants, let's smush those together and just call that C. Okay, when you have two natural logs added together, that's the same as the natural log of x times y. Right, a fun natural log trick. So the natural log of x times y. How do we get rid of natural logs? With the exponential. So e to the natural log of x, y equals e to the c. Let's call this equal to, I don't know, C3. It's still a constant, it's still arbitrary. Okay, so now we have x times y equals C3, which gives us y equals C3 over x. So these are this is our equation for streamlines. And why do we have a constant that's arbitrary hanging out there? Well, if we went back up to our picture, and you'll actually go through and plot some of these as homework, but if we were to go through to our picture up here, we're going to have, say, one streamline that goes through that point. Maybe it looks like this. We're going to have another streamline that goes through there, another streamline that goes through there, another one that goes through there. Each of those individual streamlines will correspond to a different unknown constant. So each streamline has a unique value of C, or I guess how we called it C3. So that's why we end up with this unknown constant. So when you're doing the integration and doing this, you can't forget the constant, because it actually turns out that that's a really important part of the streamlines, because we should have an infinite number of streamlines with each one corresponding to a different value of some unknown constant. Okay, the last thing that we're going to do, so we can figure out the velocity anywhere, we can figure out what the streamlines look like. We can also use the velocity field to track where things are going and like look at fluid particle motion. So we could answer a question like is at 1, 3. So at this position at time 0, I'll put a line there so we know that this is a different question. So we're starting at the point that we started at before, but we want to ask where is this at t equals 4 seconds. So not only what is the velocity when it's at this exact point, but where is it going to be 4 seconds later? Okay, so we can answer that question with the velocity field. Our velocity field is ax I hat minus ay j hat. Right, this is the x velocity. This is the y velocity. Okay, another way of saying the x velocity is dx dt, right? The change in x d time. So u equals dx dt, which in this case equals ax, and v equals dy just from the definition of velocity, ay. So if we want to find the position, yikes. Okay, so if we want to find the position at t equals 4 seconds, let's first look at the x position. Then we'll look at the y position. So the x position, we're going to look at right, we have dx dt equals ax. So we're going to, again, separate variables and integrate. So let's get the x's on one side and the t's on the other side. So this goes to, we'll just divide both sides by x. So we'll get 1 over x dx equals a dt. Then we can integrate 1 over x from x0 to x1. That's our new position, or from x0, we'll call it just to x. X0 being our initial position, x being the final position, equals the integral from t0 to t of a dt. If we do this integration, the one on the left is natural log. The one on the right is a times t. So this gives us the natural log. This would be of x divided by x0 equals a t. And then we can solve for x is equal to x naught e to the a t. Okay, if we just do some rearranging. Okay, so the cool thing about having a velocity field, so if we have a mathematical description of the velocity field, we know all of the things that we might want to know. And we'll come back later and say there's actually even more that we could know. We could know like flow rates and forces on objects, and we can calculate all kinds of different things about the fluid flow if we know the velocity field. But we can figure out like what's the speed at any given location, how far are things moving, if they start somewhere, where do they end up with, what does the flow look like visually. We can calculate all of that type of stuff from this kind of basic velocity field information. Okay, if we go through, I guess let me get another page, and then we can get put some numbers to this, and then we'll be done for the day. Okay, so that would be our x position, our y position. Yeah, Theo.
Why are we calculating position?
So this is, we'll draw it in a second. Okay, so if we wanted to find the y position, at time t, we would do the same thing. This would be dy dt equals minus ay. we would do an integral from y naught to y 1 over y dy equals the integral from 0 to t of minus a dt. And so it looked basically the exact same, except we have a minus sign thrown in because our u and our v, like the x component and the y component, are basically the same, except this one has a minus sign thrown in. So that's why it turns out to be basically the same. If we were to solve this, we would get y equals y naught e to the minus a t. So if we wanted to find our position, right, we wanted to find position at 4 seconds. If we started at 1,3. So let's draw what that would look like again. This would be our y-axis. This would be our x-axis. We're up here at 3, down here at 1. Right, remember initially we're going in this direction, v. Our final position at 4 seconds would be x of 4 seconds would be equal to 1 times e to the at, so this would be 0.3 seconds inverse, seconds to the -1 times 4 seconds. And our y, let me write it this way. X of t equals 3 e to the minus 0.3 per second times 4 seconds. So our final position would be, bust out my calculator. So that's going to be e to the, here's my e to the 0.3 times 4. Nope. E to the 0.3 times 4. So my final x position is 3.32 meters. My final y position is to the negative that. So this is 3 times, well, 3 times e to the minus 1.2. My final y position is 0.90 meters. So I start here. If we wanted to track my path, I would go along there. And I would end up, so this is at t equals 4 seconds. I'm now at, this is 3.32, 0.90. So I would travel along one of the streamlines, and I can figure out then from, you know, how much time has elapsed, how far I've actually moved along that streamline. So there's a lot that you can do if you have a description of the velocity field. The challenge is, how do you actually come up with that description of the velocity field? And that's where some of the kind of more fun parts of, or at least for me, more fun parts of fluid mechanics is we're going to have to think of, okay, what's actually moving the fluid? it's being moved by forces. What types of forces? How are they acting? How can we handle all of this stuff? So we're going to do some of that, but hopefully this gives you some sense of why. We're going to do a lot of stuff like why do we care about the velocity field? Well, we care about it because if we know it, we know everything about what's happening, so we can figure out anything that we need to. So we'll keep messing with this, but hopefully this gives you some sense. This should give you enough stuff that you can tackle all of the homework. So you should be all set for that, but we'll come back next week and we'll talk more about forces on fluids and how fluids behave. And so happy Friday. Hope you have a good weekend.
Thank you.
Yeah, I'm excited. I'm very excited.